That's the type of idea. If a vertex goes down, you're looking at something like that. Good. Question 5. If edge x6, x7 is removed from each of the graphs in exercise 2, do we still have Hamilton circuits? So, x6 is there, x7 is there. In part A, we're looking at this, and I want to know, do I have a Hamilton circuit? Well, these edges would have to be included because it's degree 2. These edges because it's that vertice, and these edges because of that vertice. So now I'm just wondering, can I connect the rest of this stuff without violating a Hamilton circuit? From here, I would have to go to x6 and leave, or go to x6 and leave. However I connect these things, I can't do it without making a circuit on this side. And the same thing over here. I can't do it without making a circuit on that side. So, no Hamilton circuit is possible. That was the question, right? Yeah. Do the resulting graphs still have Hamilton circuits? The answer for part A then is no, because however I connect these, I would have to make a circuit. Yes. And then B. x6 was here and x7 is there. So now x6 is valence 2. So I must use those two edges as part of a Hamilton circuit. Other than that, there's really no constraint, I don't think. So let's think about it. I could go out here and kill those two and come back here. Then I've got to go there, and it seems like I can connect things. So I'll do that. From there I went out to x7, here down there. And that is really hard to see, but it is a Hamilton circuit. The one piece of your Hamilton circuit that must match is these two edges would have to be in it. Other than those two edges, any way you could go around and touch every vertex without revisiting one would be fine. In C, x6, x7 was here, valence 1, so it is not possible. No Hamilton circuit possible. Good. That was 5A. 5B. I'm looking up here, 5B. If you think of the graphs in exercise 2 as communication networks, one interpretation might be given to removal of an edge, as described in part A. Well, as opposed to removal of a vertex, like in part 4, now I'm looking at the removal of an edge. So, those edges aren't like, it's not like the computer, x6 or x7 crashed. The line between them went down. So if this was something delivering a physical object, maybe that's one of the vacuum tube type of things that you see at the bank. Or maybe that edge means like some of the wiring went bad between here, or maybe there was an earthquake and like some line went down, but each building or each computer or each whatever these nodes are, they're fine. It's just the connection between them has crashed. Maybe there's some sort of software virus crashed that. Anyway, whatever type of thing you were saying down here would be fine as long as you're saying the actual nodes, and what I mean by that are the computers or the buildings, are fine, but for some reason they can't communicate. And we don't know why, but for whatever reason, those nodes are still there. They can't communicate with each other. That's why the connection between them is gone, but each node still exists. 6A. Give examples of real-world situations that can be modeled using a graph and for which finding a Hamiltonian circuit of the graph would be of interest. Well, you can't see the whole problem. Well, the answer really is any time that we care about visiting multiple locations. So, real-world situation, and it may be contrived, but the traveling salesman problem is one real-world situation where a traveling salesman has to visit different cities and make it back home. Another one would be, I don't know, picking up friends for some reason. Picking up friends. Another one could be, well, dropping people off. Another one could be you're looking at a telephone network. And what I mean is this is the telephone company actually looking to make sure all of the lines are connected. You as a consumer wouldn't care about the telephone network at all, but the company would be trying to make sure that everything is connected, because if they're looking at 3 different cities that they're going to be making calls between, maybe there are lots and lots and lots of calls between this and that city. If that line gets overloaded, then all of a sudden it doesn't exist. Well, they want to make sure there's other connections going on, because if this line is overloaded, they can relay all the calls through a 3rd city. Anyway, any type of thing where you're looking at visiting different locations, emergency responding possibly, I don't know. Lots of different things for 6A. 6B, for each of the examples you mentioned part A, can you adapt the question about the real-world situation so that finding an Eulerian circuit in the same graph would be of interest? So what happens is, instead of visiting the different locations being of interest, we care about visiting all of the lines between those locations becoming of interest. This is far less common. Eulerian circuits are interesting because we actually have easy ways to solve them, but really it's usually very difficult to adapt these things to make them into Eulerian circuits. But if you were going to adapt them, it would be, instead, for some reason, instead of the actual locations, T-I-O-N-S, being of interest, the connections are the interesting piece. It's far less common, but instead of the locations being of interest, you'd be interested in the connections. Then problem number 7. Okay. Suppose 2 Hamiltonian circuits are considered different if the collections of edges they use are different. How many other Hamiltonian circuits can you find in the graph in figure 2.1 that are different from the 2 discussed? So there's the figure 2.1. The 2 discussed, I think, were like you go in and around there, and I think there was one where you go in and go around these and then go out and go around those. I think looking at this, it's really hard to tell. My first thought was this would be simple to talk about, but I may be wrong. Okay, so we've used, I guess, let's go ahead and look at which 2 they were. Oh, here's figure 2.1. Well, okay, I can draw them on here. We're looking at this circuit. And they used this circuit. Okay, so other circuits, well, sure. Sorry, this is a much more annoying problem than I thought. It would be different if I went like all the way around, all the way around the inside and then came out and went all the way around the outside. So that's one. I could do the reflection of that. So instead of going around the inside here and then around the outside here, I could go around the inside here and then around the outside there. I think those are the only two that I see. It's possible there are more, but those are the two that I see. If I draw this part, okay, I see this one. Oh, whoops, not that edge. Around the inside and then around the outside. And I see the reflection around the inside and then around the outside. I don't think I see any others. I see exactly those two. Yeah, it seems like this video is getting fairly long, so I'm going to make a second video for the other piece. For the second half of this assignment, numbers 9 through 13. Thanks.